Nobody really wants to listen to me read boring PowerPoint slides to you. So we want to talk about this subject here first and talk about pH. And as I told you the other day, all of our acid-base equilibria is occurring in water. So this autoionization of water is important. What might that look like? So water, to a small extent, ionizes, and Kw is 1 times 10 to the negative 14. So that's a small number. What is the hydronium concentration in pure water? So we'll approach it like we approach any ionic equilibria. We'll say, let's just imagine we have our liquid, and somehow there's none of these two things. Well, a change is going to occur. Some of this goes away, some of this forms. So then we say, how much? We don't know. Oh, looks like I got ahead of myself and put X there. So there's what an ice table might look like for this process, which is going to help us answer this question. So now what is the next step? I got my ice table. I have my equation showing the equilibrium. I have my equilibrium constant. We already got it. Yeah, solve for X. So the thing missing is the equilibrium expression. What is the equilibrium expression? Kw equals what? I heard half of it correct. It's going to be products over water, but what did you learn about heterogeneous equilibrium? Here we have a pure liquid. Doesn't show up. So this is how it looks. So the next step is to plug in the bottom row of the ice table into the equilibrium expression. And this is going to give us something that looks like this. X times X is X squared equals Kw. Alright, why don't I take the square root of each side? And since I'm running out of whiteboard real estate here, I'm going to just put in Kw. 1 times 10 to the negative 14th. So if you know your exponents real well, you can do the square root of this without a calculator. What's the square root of 1 times 10 to the negative 14th? Yeah, absolutely. 1 times 10 to the negative 7th molar hydronium ion. So we've answered this question. We can say hydronium ion. Now, who wants to write all those zeros? 0.00000001. Alright, so we have a more convenient way to do things. How many of you have ever heard of this? pH. What does pH mean? This stands for power, like exponent. So negative log. Alright, pull out your calculator and go negative log of 1 times 10 to the negative 14th. And what does your calculator spit out? That would be right. Yeah, negative log of 1 times 10 to the negative 7th is what? Does that number sound about right? Any of you keep an aquarium, have a hot tub? What's neutral pH?
7.
7. Absolutely. Alright, we're probably going to come back to this in a little bit. A Bronsted-Lowry acid is a species that donates a proton. Bronsted-Lowry base is a species that accepts a proton. And this is what we looked at on Monday. I said ammonia is a Uranus base. Because you put it in water, you increase hydroxide ion concentration. The Bronsted-Lowry definition says a base is a species that accepts a proton. Where did the proton come from? It came from water, and that's why we now have the ammonium cation over here and hydroxide. And on Monday I wrote up the term conjugate on the board. It comes from the Latin word conjure. Sounds like a magician to me. I'm probably mispronouncing it, meaning to join together. Reactions between acids and bases always yield their conjugate bases and acids. Alright, is this a strong acid? No, because you know nitrate is HNO3, and here we have some HNO2. It's not on that list of 7. And you can say, well, of course not, Eric. There's the equilibrium arrows. So it protonates water, which is our base. And there we can see the hydronium ion. And we can imagine If we knew that concentration, we could put it into pH equals negative log, and we could see an acidic pH. Here's what you want to remember. Whenever you want to assign these things, conjugate acid-base pairs differ by only one proton. So this thing and this thing differ by one proton. Nitrite ion and this nitrous acid. Here's water and here's hydronium. They differ by one proton. These two things differ by 3 protons. So a lot of times this will keep you from getting tripped up in assigning conjugate acid-base pairs. Strong acids are completely dissociated, and their conjugate bases are quite weak. I like to call them worthless bases. Weak acids only partially dissociate in water, and their conjugate bases are weak. Number 3 has a couple different variations, but it's a sentence you kind of memorize and pull it out whenever you need to apply it. In any acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base, or it sometimes says in an equilibrium always favors the formation of the weaker acid. There's a couple ways to say that. Like I said right there, always favors the formation of the weaker acid. So here's HCl. In water, it completely dissociates, so no equilibrium arrow here. And we have the hydronium ion and the chloride ion. And if we apply this base concept, we say H2O is a much stronger base than the chloride ion. So equilibrium lies to the right. And we don't normally associate a K value with something that completely disassociates. So here's HCl. Notice these are all strong acids. You find these 3 in that list of 7. Since they're strong, once they donate a proton, what's left over is the conjugate base. And so chloride, a worthless base. Nitrate, a worthless base. We say these have negligible basicity. And all these acids here form hydronium in water. The conjugate base of hydronium is H2O. So down here in the middle, here's HF. It's not in that list. We know it's a weak acid. And so something like sodium fluoride, potassium fluoride, fluoride ion, you put it in water, it's going to form hydroxide. It's going to behave as a base. We say it's a weak base. Here's a little organic chemistry. An alkane, like CH4, is the weakest acid known to mankind. So if I pull a proton off, I'm going to have this methyl anion here. This has got to be the strongest base known to mankind. I wrote acetate a little different over there on the board. This is acetic acid thing in vinegar, and acetate is a polyatomic ion. You should have learned in Chem 1. Where does equilibrium lie over here? Maybe we don't know anything about this reactant side. So we look over here and we say hydronium ion. That was way up on the top of that list. That's a strong acid. We're going to pretend we don't know anything about this acid. And then we look over here and it says acetate is a stronger base than H2O. So we want to keep the weaker base and the weaker acid. So here's what we looked at with my example equilibrium problem, is the autoionization of water. So here's 2 water molecules. These electrons grab that proton, those electrons jump back on oxygen. So here's this charged species called hydroxide, and here is the hydronium ion. Pure water, the following equilibrium is established, and this is referred to as autoionization. The equilibrium expression for this process, presently here I got a C, meaning concentration, meaning molarities here. This special equilibrium constant is referred to as the ion product constant for water. Here's the ion product. This thing times that thing equals Kw. And Kw applies to pure water as well as aqueous solution. So how do we know if a solution is acidic or not? Well, when it's neutral, hydroxide and hydronium equal each other. And notice here, what's the concentration of hydronium in pure water? Our ice table said it's X, and we solved for X. X also equals hydroxide ion concentration, and that's going to equal the same molar concentration. So when hydroxide and hydronium ion are equal, we have a neutral solution. If we have more hydronium than hydroxide, we say it's acidic. If we have more hydroxide than hydronium, we say it's basic. Now, since hydronium and hydroxide ion can vary over a large range, it's more convenient to come up with a logarithmic scale. And that's what pH is. It's just a logarithmic scale, and we can cover a great span with just a few numbers, 1 through 14 perhaps. And P might stand for power of the hydronium ion. Bring that up here in a second. And so here's what we solved with our ice table. This thing holds true anytime you're dealing with water. And you could have a bunch of salt, you could have HCl in there. If you put a bunch of HCl, that's going to raise hydronium up. And if hydronium ion concentration goes up, what has to happen to hydroxide concentration? Yeah, it's got to hold down, because this product is always going to equal 1 times 10 to the negative 14th. So how do we know if a solution is acidic? If an acid has a hydronium ion concentration that's higher than what it normally is in pure water, we say it's acidic. So a pH less than 7. And so here's our neutral. They're equal in concentration. Here's something that is acidic, and here is basic. So pH of 9, that's basic. pH of 14, that's real basic. pH of 6, that's acidic. So other P scales, P in pH tells us to take the negative base 10 logarithm of the quantity, in this case hydronium ions. So before today you probably never heard of POH. Well, POH is negative log of hydroxide, or pKw. Well, that's the negative log of Kw. Can anybody tell me what a pKa is? Like an organic student. We talk about pKa. I just got a dirty look. Yeah, our equilibrium constants can vary quite a bit. And who likes dealing with that scientific notation all the time? 2.5 times 10 to the negative 8th. Sometimes we like whole numbers, or 4.2, 7.8. So here is a favorite slide of mine. I suppose it's my favorite slide because it tells me you don't want to let your sick friends barf out the window of your car, because stomach acid is 0.1 molar HCl. That's today's humor. But notice we have everything tied together. So Kw is called the ion product. Here's hydrogen ion times hydroxide ion, and it equals 1 times 10 to the 14th. We can logify this equation. I don't know if your math teachers ever say that, logify. pH plus POH equals 14. And if I look up here, let's just go back to our stomach acid. I wanted to do this on the whiteboard before I ran out of time. What is the hydroxide concentration in your stomach? And it's still alright. We'll just write this out as a nice, fun word problem. Stomach acid is 10th molar HCl, and this should lead into something coming up later with knowing the pH of a strong acid. Since a strong acid completely disassociates, that also gives us the hydronium concentration. Or we could say 0.01 molar protons. We use protons and hydronium interchangeably. So we're going to use Kw. And I'm going to be lazy and get rid of writing hydronium or aqueous symbols. We're after hydroxide. So let's rearrange this equation in terms of hydroxide by dividing both sides by hydrogen ion. There we go. So that means I got to pull out 1 times 10 to the negative 14th and divide it by 0.1. Now I'll be able to do this in my head, right? It's going to be 1 times 10 to the negative 13th. Very good. There we calculated how much hydroxide's in your stomach if you have a normal stomach. Maybe if you need a Tums, it's a little worse. And this would be a little lower. Well, since I got the camera up here, let's ask ourselves a few more questions and then we'll go back and look at this PowerPoint slide. Okay, we answer that question. You see how to calculate it. What's the pH of stomach juice? I got one Rico he knows. Yeah, that's good. What's the pH? Yeah. That's the second humorous thing to do. Hopefully. I told you to remember better if you laugh. Right, so what's our definition of pH? pH equals negative log 0.1 molar hydrogen ion. Alright, so pull that out on your calculator. That's a good acidic pH, right? What is its pOH? Yeah, what we saw for first, and that was hydroxide ion concentration. And do you remember what it was? Has a hydroxide ion concentration of 1 times 10 to the negative 13th. This number times that number is going to equal 1 times 10 to the negative 14th. So we said we know what pH is now, this negative log. And we calculated the pH to be 1, and we calculated the pOH to be 13. They sum up to 14. So here's our logified version of our KW expression. pH plus pOH equals 14. So possibly when we know the pH is 1 here, and we ask what is the pOH, we can subtract 1 from 14 and get this number here. So one side bit of information with our property of logs. This will come up somewhere in a PowerPoint slide. The molar concentration of hydronium ion is 10 to the negative pH. The molar concentration of hydroxide is 10 to the negative pOH. Hydronium concentration 10 to the negative pH. Hydroxide 10 to the negative pOH. And this is just log properties and our definition. Any questions?